Right, so there were a lot of questions about priors, and this is what we're going to be talking about now. And I think I will try also to add in, so like I had the slides prepared, but I'll try perhaps to add in more information based on the questions that you asked us. But let me share the screen first. That should be that one. Yep. Right. So before I start with the priors, this is a more general comment about Bayesian inference. In fact, we didn't really talk about this, and I don't want to confuse you now, but it's an interesting thing to think about. In fact, there are two camps within Bayesian statistics, and they're called the objective Bayesianism and subjective Bayesianism. And the idea is that if you're an objective Bayesian, you assume that each and every bit of your research and your model are justified objectively, are justified in a way that another person would agree basically with you, assuming of course that the model and framework is the same. On the other hand, subjective Bayesian inference is really about the subjective take of the researcher and how that has an effect on the research. And you don't have to choose, of course. In fact, if you read one very short paper by Gelman, I'll send you a link if you're interested. They say it's not really a matter of subjective versus objective, but about transparency and justification. So like if you're transparent about your decisions and you justify each and every bit of the decision process that you went through in designing the experiment as we would normally do, but also in defining priors, doing inference from posteriors or other methods. As long as you do that, then it's fine, because a reviewer or another person could, go through your reasoning and decide whether the reasoning is actually valid or appropriate for the question that you have to answer. And in fact, this is particularly sensitive, it's a particularly sensitive topic when it comes to priors, because in fact, what we've seen so far is that the priors didn't really make much of a difference, but they can. They can make a lot of a difference depending on how you specify priors. And that's why in this session, I will tell you about different types of priors that you can use to be on the safe side. Especially, I personally do not recommend Bayes factors, and I think Timo and Joseph feel more or less the same. Bayes factors are extremely sensitive to prior specification, even when you use very, very uninformative priors. So if you really want to do, my suggestion, my preference is not to use Bayes factors actually, but if you really want to use Bayes factors, you must calculate Bayes factors using different priors. So you will have to rerun the same model at least 3, 4, 6 times with increasingly wider or increasingly thinner priors, and we're going to see what that means in a second. So you see that it's really a lot that you have to think about and justify. Just one last thing before we move on to priors. Probably the difference between frequentist statistics and Bayesian statistics in this regard is that with frequentist statistics, you have, pass me the term, the luxury not to think about many things, because basically you just need to specify the formula and put the data in. Hopefully that will converge. And in fact, the model is choosing for you. There are a lot of assumptions in the model that you don't really have access to and you cannot really change. And in fact, you're letting the model choose for you. On the other hand, with Bayesian inference, everything is, like has to be really specified and thought about. And you will see, like, hopefully you will decide to at least try out running a Bayesian model with your data. You will see that having to think about all of these different bits and parts will basically give you a sense of how much you know about that particular topic and how much we can actually contribute about that particular topic. And in fact, you will see that in many cases, defining a rope is not that easy, or defining priors is not that easy. And that is not a it's not a shortcoming of Bayesian inference if it's potentially a shortcoming of the level of quantitative knowledge of granularity that we have reached within linguistics and within speech sciences. So if you find yourself, like, if you feel that it's difficult for you to come up with priors and come up with ropes, probably that is a sign that what we need to focus on is estimating these effects rather than knowing whether the effects is relevant or not. Perhaps Timo and Joseph might disagree on a few of these aspects, but this is important. This is really part of doing research and applying Bayesian inference on the data. Right. So sorry for the philosophical note, and let's go. Wait, Timo says we should. Yes, exactly. So Timo says something interesting, that we should forget significance. In fact, I don't know if we said it explicitly, statistical significance does not exist within Bayesian statistics. It's a concept that makes sense only and exclusively within the null hypothesis significance testing. That's why it's called significant testing. So the whole concept that we've basically been given when we do Stats 101 it's really one way of looking at statistics, one way of looking at research, and significance doesn't have a role within Bayesian inference. And we're going to tell you more about this probably throughout the rest of this day. Right, so we mentioned that there are different types of priors. And one aspect of the prior that it's important to think about is called informativity. And informativity is about how much knowledge you're basically conveying by specifying particular priors. So a prior can be very informative or not informative at all, meaning that in the case of a very informative prior, the model really is learning from your prior a lot. So like you're already taking into consideration a lot of knowledge, and we're going to see specific examples in a second. But just conceptually, informativity is about how strongly you feel about your prior choice, basically how strongly you feel about a particular effect. And in fact, informativity is a scale. So you have from the least to the greatest amount of information that can be conveyed by a prior. And note that the scale is relative, it's not absolute. So what something could look like a very informative prior for one effect, it might be a very non-informative at all for another effect. For example, think about duration. If you're looking at vowel duration, some values of possible effects will make sense for vowel duration, but as soon as you move on to word duration or even sentence duration, then of course you're on a completely different scale, and you will have to think about it in terms of that particular scale. So based on this scale, we can sort of identify three types of priors within that scale, but again, it's a scale, so there are we assign these three labels, but in fact, it's really not quantifiable, right? Informativity is quite a difficult concept per se, but generally, people talk about 3 different types of priors, depending on how informative they are. And from the left to the right, you see increasingly informative priors. And to the left, you have uninformative priors. And uninformative priors is basically a prior that doesn't convey any information whatsoever. And these are also called flat priors. We're going to see an illustration in a second, because the distribution, if you plot the distribution, it looks like a straight line and it's flat, and all of the values have the same probability. And if you're saying that any possible value has the same probability, you're basically, as Ricardo Bermúdez would say, you have information content 0, right? Because anything can happen. And that is called an uninformative prior or a flat prior. And in fact, personally, I recommend not using uninformative priors because we always know something, right? And using uninformative priors actually increases the uncertainty that the model basically gives you at the end, right? So if you don't convey at least some information in the model using priors, we can say, in practical terms, it's going to take you longer to reach the real value that you're estimating. And we're going to see how the prior and the data actually combine to give the posterior, and what happens when different aspects of the prior and the data change, how the posterior basically behaves. And we'll see that in a second. And these uninformative priors, of course, have no influence whatsoever on the posterior. Then in the middle, you have, well, actually, let's go to the strongly informative priors on the very far right. This basically means that you convey most or all of the prior knowledge that you know about a particular estimate, a particular parameter, a particular effect. And these have the strongest influence on the posterior. An example of a strongly informative prior would be, for example, to set an effect of differences in value duration to be any value between, for example, 30 milliseconds and 40 milliseconds, right? So if your prior for differences in value duration is that, precise and that thin, it means that you're conveying a lot of information into the model. And in principle, you could do that if the framework or model that you're testing or using to do research, if that model and framework actually tells you, based on all of these assumptions, based on all of the expectations from this particular model, I should see a difference of, like 30 or up to 40 milliseconds and nothing else, then indeed you could use potentially strongly informative priors to test that particular idea. For example, you cannot really do that with frequency statistics. Frequency statistics is just about rejecting the null hypothesis, right? So if the model, if your favorite model actually allows you to be that specific, then absolutely using strongly informative priors can be a way of testing that idea that you should get an effect that is exactly within that range. If that's the case, then of course you should also try the same model with weakly informative priors. And weakly informative priors are priors that convey some of the knowledge that we have about the world, basically, but it's vague, or at least less informative than what the actual knowledge is, right? So a weakly informative prior is basically a prior that tells the model, that nudges the model towards values that we think are probable, but it doesn't constrain it as much as a strongly informative prior would do. And as a general rule, we could say that if you go with weakly informative priors, you go safe because they will have some, and we're going to see they will have some effects on the posterior, but not so much as to actually the equivalent of p-hacking, basically, as somebody asked in the question time. So weakly informative priors are just general priors that convey some of the information that we know about a particular estimate, but not all of it. And after the conceptual part here, you see some concrete examples. Here we go back to fundamental frequency, which is probably easier to think about than articulation rate. So what you see here are 4 different priors with increasing or decreasing informativity. And of course, on the x-axis, you have hertz. That's how we measure frequency, fundamental frequency. And if you look at the orange line, that doesn't have any information whatsoever. It's saying any value from -infinity to +infinity goes. So we know nothing about what F0 could look like, right? And that is a flat prior, as you see, as I was saying before, like it looks like a flat line. And with that prior, you're not conveying any kind of information. If we go with the light purple prior, that is a weakly informative prior, because it basically tells you that any value between about 0 and 400 hertz is plausible, for example, for the mean of F0, right? So if you think about the mean of F0, you could say, yeah, like something in between 0 and 400 might make sense. And this is the mean, right? This is the prior on the mean, which means that you could get potentially values that are higher than 400. But here we're talking about the mean specifically. If you're wondering about the negative values, we're going to see that. We're going to see how to fix that in a second. So again, sorry, but we're not done. A strong prior here would be this one, where in this case you could have values between 100 and 300, and in that case you're basically saying that any value above 300 is not really a plausible value for the mean F0, while anything below 100 is not really a plausible value for mean F0. If you're wondering about if you have predictors in the model and you're using contrast coding, then the mean, which is the intercept in the model, will be related to the reference level of those particular terms. But this is basically the same as with LBER, as with frequency statistics, right? The difference is that we don't have to set priors, but the intercept will contain the reference levels if you use contrast coding. Sorry, Friedman contrasts. And instead, if we go to a very strong prior, in that case, it's this very, very thin and tall prior where we're saying that we're expecting the mean value of F0 to be anything between 150 and 250. And I'm sure you can understand now that that is a like very strong informative prior, because that's a very, very tiny range of all of the possible values that F0 could potentially get. And in fact, we know that the range of F0 for human speech is quite large, and in fact, this might be, like a very, very formative prior, and potentially also centered on 200 hertz, which might not be the best value. And in order to be able to know which is the best, center value and how wide the prior should be, you have to get that from prior studies or pilot data, as we were saying before. Power analysis potentially, or just common sense, or domain expertise, right? So like if you work, for example, am I correct to think, yes, that I don't think I've ever worked directly with fundamental frequency, perhaps with formants, but not really. Most of my work is actually about durations. So, you know, like I got a very good sense of what plausible values we might get with certain effects, with certain phenomena. But for F0, I wouldn't really be, you know, like that confident. So if you work on prosody and you work on fundamental frequency, I'm sure that you will be able to, you know, like say, yeah, I mean, this weakly informative prior that you say it's weakly informative, perhaps it's not that weakly informative. And if you remember, like what we were saying yesterday, you can, in order to sort of explain the prior and quantify the prior, you can use the 95% credible interval, and that is the mean plus twice the standard deviation, and the mean minus twice the standard deviation, right? So you can reason that way. You can say, as a prior, we set I don't know, a normal distribution with a mean 200 and a standard deviation of 100, because we expect at 95% probability that the mean is within this range, which is basically 0 and 400, right? Because if the standard deviation is 100, twice is 200, and if you add that to the mean 200, you get 400. If you subtract it, you get 0. Sorry. So this, you know, like setting priors really has to be built on top of your knowledge about the phenomenon that you're looking at. And trust me, like it wasn't very easy for me to really, you know, find a lot in the literature that would help me come up with priors, because in order to be able to do that, you really have to look at the estimates, at the effects of the size, at the size of the effects that are reported. And sometimes, especially in older literature, and it just so happens that most of the literature that I had to look was actually prior to 2000. So it's interesting to see that most of, you know, like the very important literature that we know about, in fact, most times doesn't really give you estimates. It just tells you we found a significant effect and the val is longer. And you cannot really do anything with it. Like you cannot really use that qualitative description to a, in fact, quantitative result. So that's why it's always very, very important. And now I think it has become common practice to report not only if you use frequentist statistic, the p-value, but also the effect, the estimated effect. Let me see if there are some questions that yeah, exactly. Yeah, not uniform distributions. So basically, what happens is that. So let me give you a stupid example. Let's assume that the real value that you're looking at is that I don't know, politeness decreases fundamental frequency by 50 hertz. It's completely, you know, bonkers. Like I'm just making this up. And you start, you know, with a flat prior. That means that, you know, like even though the real effect is minus 50 hertz, you're saying any value, you know, could do. So even plus 1,000 hertz or minus, you know, like a million hertz, right? So what happens is that uncertainty about what possible effect you're looking at, what the possible value of the effect is, that uncertainty will be transferred onto the posterior. So what that means is that your posterior is going to be wider. Your 95% credible interval is going to be wider. And that just means that we will need more time and more studies to reach the real value that is 50. And that's why it's not recommended to use uniform priors. A practical aspect of not using, a practical reason for not using uniform priors is also that that might actually lead to problems with sampling, with the sampling procedure that Joseph is going to explain in details later. But using an informative priors, flat priors like this one in orange, will actually increase the chance of having issues when fitting the model. So that's why weakly informative priors are really the way to go. And again, weakly is really a relative term. There is no a rule of thumb. It really depends on the measurement that you're looking at, duration, F0, I don't know, gestural velocity or anything. And on top of that, also on the specific effect that you're looking at, right? So if it's file duration is one thing, if it's sentence duration is another.
There's one question, Stefano, which I think is useful to answer. So if someone asks, and that someone is usually the reviewer that we have in mind, asks us about the informativity of our prior, we can't give them a clear-cut answer. How could we justify the difference between a weak and a strong prior?
That's, again, like, these questions are brilliant because like they really show how much thinking needs to go into defining priors. But this is great, you know, for linguistics. This is great for speech science, for science in general, for research. We really need to think a lot about this. And in fact, that's also why, you know, like I am personally a subjective, like, you know, like I ascribe to the subjective camp of Bayesian inference. You really need to think in terms of what we know about that specific effect or that specific parameter that you're estimating. And one person might disagree with you, might say that that is actually not particularly weak. It's actually stronger than you claim, you know, and then you really have to justify why you think that's the case. We're going to see examples actually of what, you know, like how you could potentially assess in a less subjective way what a weakly informative prior would look like. But that's absolutely a great question. So yeah, unfortunately, there is no straightforward answer. And that is because the models that we work with, the frameworks that we work with, compared, for example, to frameworks from physics, they're new, they're more recent. And in fact, they haven't reached that mathematical precision that, for example, models from physics have. That's why it's difficult for us to, you know, to say, okay, these values are sensible, those are not. But it's changing now. Like if you look at work that uses Bayesian inference, you can see that, you know, that we're getting more and more. We're getting a better idea of what these actual estimates are. So I think, you know, I think this is an exciting opportunity actually to advance the knowledge that we have about speech in general, about language, and we can do so in a way that it's, you know, like how can I put this, like more orderly. Like it's not just about saying whether there is an effect or not, but it's about how big the effect is. And the effect that I found in this study is way smaller than the effect that the other person has found in like basically the same study with different participants. Why is that the case? And we can really start thinking about that and what that means for the model and the framework. Sorry, that was a long detour. And of course, each parameter in the model has its own prior. So for each parameter, you will have to think of the prior, right? For the intercept, for the class B priors, so the priors for the predictors that you put in the model, you will have to think about the standard deviation of the intercept and of other parameters that might be relevant depending on the model that you use. So which priors you have to set depends on the model, right? And you will have different parameters to set priors for depending on what model you're actually running.
We should, unfortunately, this is obviously at the core of this interesting new tool, and there's much more to say about that. Unfortunately, we need to move on.
So I think all of what I said before, like, it's really relevant, but another thing that we recommend using is regularizing priors. I won't be able to show this to you now, but regularizing priors are simply priors that have the mean set at 0. And if you remember, I told you that yesterday, that if you set the mean of your prior to 0 and you focus on the standard deviation, you're fine, you're going to be fine. So what really matters is the standard deviation of the prior if you're using a normal normal distribution for the prior. Very briefly, there's a way of doing so-called prior predictive checks. It's quite easy, like you basically just have to run that code. You can actually look at the code on the slides, and you can plot that simply with, it's very, very simple. Once you get the output, you can plot this with conditional effects. And what you see here is the predicted possible values based on the priors that you have specified for the outcome variable. And here we're looking at articulation rate. And you can see that based on this model and priors, articulation rate could be anything between like a -30 and +30. This doesn't make any sense because articulation rate cannot be negative, and that is because we've been using the wrong family. So if you look here, I specified a log normal distribution that doesn't allow negative values. So now actually you can set priors on the log scale, because this is a log normal distribution. So this is a bit tricky. But we can go into this perhaps on Monday, and then we'll give you more concrete examples. And if you plot it now, like, it looks great in the sense that you don't have negative values anymore, but you do have very, very high values. Like, basically you're saying that based on the priors and the model, you could even get more than 1,500 syllables per second, which is not great. So this is very, very weakly informative, if probably not informative at all prior. I hope I didn't confuse you with this going quite quickly, but I'm done. So we can now, I guess, go on to sampling and what actually the model is doing when you see all of those messages about chains. No,
we're not.
Oh, sorry, no, stepping out, sorry.
However, we should consider, so there are, just for expectation management, there are 3 sessions left. There is a coding session with me now on linear mixed effects models, where we level up a little bit. And there's also a planned exercise, which you might throw overboard, but the materials are there. So you can go through the walkthrough, you can go through the exercise that are prepared for you. We also have what Stefano just mentioned. We have the sampling from the posterior that we want to look at. And we have a wrap-up session at the end that summarizes, that provides some more resources, and that gives a little show reel of what you can do with BRMS if you want to.